All right, today we covered Chapter 4, Section 2, which is types of waves. So just to review quickly, we said that the anatomy of a wave consists of 4 parts. You have the crest is the top of the wave, the trough is the bottom of the wave, the height is the difference between the trough and the crest, and the wavelength is from one crest to the next. Now that's going to be important in the definitions we're going to look at now. There's 2 types of waves generally. There's deep water and shallow water waves. They have different characteristics and they travel differently through the ocean. They depend on the depth of the ocean and the wavelength. So if you look at the diagram here, let's take a look at the deep water waves. Deep water waves, if you look at the circles there, underneath the circles you'll see a line that says no wave motion. And what that means is that if you were swimming, let's say you were a sea lion and you were swimming down under that white line, you wouldn't feel the wave. But if you swim above that, where the circles are, you would feel the wave motion pass by you. So deep water waves have a point at which there is no wave motion. And that depth is usually at 1/2 of their wavelength. So in order to be considered a deep water wave, you have to be in water that's deeper than half your wavelength. Because what happens is, as waves approach the shore, you'll see what's going on here. As the wave is approaching the shore, the bottom of the wave begins to feel the bottom, the sand, or coral, or whatever's there, and it begins to slow the wave down. And what happens is the bottom of the wave will begin to slow down, but the top of the wave is still going faster. And so at some point, the top of the wave is going to tip forward and then break over on itself. So we call shallow water waves at which the water depth is only, it's less than 1/20th of the wavelength. So we're talking about pretty shallow water. So again, deep water waves travel in water deeper than 1/2 of their wavelength. And below that 1/2 of the wavelength there's no water movement, as you see again in the diagram. The speed of the wave depends on the wavelength and not the depth of the water. So at this point, the depth is not affecting the wave at all when it's considered a deep water wave. It's generated by wind and it's restored by gravity, and it typically moves in a particular direction. There's 2 kinds of deep water waves. There's the progressive wind waves, which is what starts out immediately when the wind starts to blow, you get progressive wind waves. But over time, those will smooth out and become rhythmic swell waves, which then will approach shore at some point. This particular picture here on the left is not a good picture because this is a wave that's breaking, which means that it's close to shore, and that would not be a deep water wave. All right, shallow water waves, again, travel in water that's less than 1/20th of their wavelength. So this is very shallow water considering the wavelength of the wave. Their speed is now dependent on the depth of water and not the wavelength. So they begin to slow down as the water gets shallower because the seafloor starts to pull on the wave and slow it down. But the top of the wave is going a little bit faster, and so that's why it begins to tilt forward, as you see in the picture there, and eventually it will break at some point on shore there. Now, one other thing that's important about shallow water waves is, remember how we said that the water particles are actually just going in a circle at each point in the wave? They're not really traveling with the wave. They are traveling in a circular motion. But as the wave gets closer to shore and begins to be affected by the bottom of the ocean there, the seafloor, then the wave particle shifts to a more elliptical pattern. And that, again, is why the top of the wave begins to lean forward and will eventually break. And when it breaks, we call that white foamy stuff surf. Now, another interesting thing is that when you're standing there and you look at the water coming up towards you at the beach, does it usually come straight at you? Does the wave come straight at the beach, parallel to the beach? No. When you see the waves, they're usually coming in at an angle, slightly left or slightly to the right. And that's because waves are refracted or bent as they move from deep water to shallow water. When they're deep water, as you see in this picture, when they're approaching land, they are parallel. They're coming straight to the surface. But once they begin to slow down, remember the bottom of the wave slows down first, the top of the wave is going a little bit faster, and that causes the water to slightly shift and come to shore at an angle. It's called wave refraction. And I just explained it again here. When the bottom of the wave slows down as the water gets shallower, the part of the wave that is in the deeper water is slowing down, and the top water is still going at that original speed, and the waves bend along the surf. They're not parallel to shore anymore. They can also give a pretty interesting pattern as they wrap around an island, depending on the seafloor under the island. All right, one more thing we want to point out, something called longshore transport. If you've ever been at the beach and you go out in the water for a little while, you're hanging out there, and then you look up, your umbrella is typically not right in front of you anymore, is it? Your towel is not where you left it. Usually you've moved, right? You've drifted a little bit in the water. And this is due to something called longshore transport. Remember that the water is hitting the beach at an angle. So as the water comes up and goes back and comes up and goes back and comes up and goes back at an angle, it is pushing things down the beach. Flip-flops, seaweed, sand bucket, sand, all get moved slowly down the beach in whatever direction the waves are approaching. Same thing happens in the water. As the waves go up and the waves go down, the waves go up and the waves go down, they're pushing things in the water as well. Seaweed, the water, you, if you're standing there, and you get moved down the beach in the direction of the waves as well. So the combination of this happening on the beach, which is called longshore drift, and in the water called longshore current, both of those together are known as longshore transport. All right, two last things we want to look at, and the first one is rip currents. You've all heard of rip currents. What are they? Well, they're actually areas of where the water is now is moving away from the beach. It's going seaward, and it's flowing out to sea, which is hazardous to swimmers. They're not big, wide, the whole beach is not a rip current. It's just these narrow currents that form at places along the beach, and it's usually due to the water being a little bit deeper in that area, so that once the water washes up, it kind of turns and it finds that slightly deeper area and begins to move back out, forming a current that takes you back out into the ocean. They also aren't really long. So if you do get caught in one, it's not going to take you a mile out or anything like that. They're usually about 300 feet possibly in length. They don't pull you under necessarily, but if you fight them and you're trying to swim back in the current, it's going to be very, very difficult. It's not recommended at all. It tires you out, and then you can drown because you just can't keep yourself up. So those currents can flow at a speed of 5 miles an hour, so they're really, really strong. So what's recommended instead is that you flow to the right, or that you swim to the right or to the left, because again, these are narrow currents, so you could swim out of them and then come back to shore. And there's a couple of videos you could check out here if you want. All right, lastly are tsunamis, which we talked about briefly the other day, but they are caused by sudden movements of Earth's crust from earthquakes or underwater volcanoes, also known as seismic sea waves, because seismic refers to earthquakes. They do a lot of damage to coastal areas because it's just one giant wave coming in to the beach, and it carries a great amount of energy. So what happens is that as the wave approaches land, all the energy in the wave goes into the height as the bottom of the wave begins to drag on the ocean floor. That pushes all the momentum upwards and makes a huge wave that then comes ashore with all that energy, causing an incredible amount of damage. Another thing that's kind of interesting about them is that when they're on the open water, you don't really notice them because it's just like maybe just a little rise in the water. That's it. It's not until they reach shore and they begin to be affected by the seafloor that the wave actually gets its height. So there are some videos you can check out online that show what I'm talking about. All right, that's it for today.